Welcome to this TIBCO Spotfire analysis on production optimization of natural gas wells. This analysis studies a collection of gas wells from the Fayetteville Shale Play near Arkoma Basin, Arkansas. Most of the wells studied are horizontal gas wells. Part of the production optimization is the well completion stage, where hydraulic fracturing is performed using fluids and sand. A critical part of well production optimization is deciding where to drill a new well. The future production of a new well is often found by studying nearby wells. The production from a well or a group of wells is forecast into the future using a smooth curve. The measure of production is the EUR, or expected ultimate recovery, which is the area under this curve. We will use Spotfire and S+ to analyze the current well data and predict the EUR of potential well sites. Let's look at a map view of the Arkoma Basin with the 1,822 locations colored and sized by EUR. The production optimization task is to find the best location for a new well and the best accommodation of completion parameters such as the well length, number of frac stages, and so on. When we mark the data on the map, the visualizations below update. The lower left is a histogram of EUR. This histogram is asymmetric with some long tails. The lower right is a scatter plot of EUR as a function of number of hydraulic fracture stages to look at how the completion parameters affect the production. There are 2 pages studying FSD, or field size distribution. First, let's look at the parametric methods of predicting probability of EUR. When we have a possible site for a new well identified, we can select some nearby wells to study their production. The EUR of the proposed well will likely fall in the same histogram or distribution as these nearby wells, and this characterization process is known as field size distribution, or FSDing. The shape of this histogram is modeled using one of the distribution families, log normal, gamma, or Weibull, resulting in a probability plot shown here on the right-hand side. On this plot, each observed well's EUR is shown as a dot. The EUR is on the y-axis, sorted from smallest to largest. The x-axis is the probability that the EUR is at least this amount. This graphical method is very common in the industry. These 3 bold vertical lines mark the 90%, 50%, and 10% probabilities that the production is greater than this amount. This straight line is a generalization of the histogram using the distribution family, in this case, the log normal. The corresponding EURs where this line intersects the y-axis are known as the P90, P50, and P10 values for EUR. These numbers are very important in the industry, for example, when reporting the well value to the SEC. Often the data points roll away at the lower and upper parts of the plot, meaning that the tails of the histogram are not well modeled by this family. These are precisely where you need the best accuracy, at the low and high ends of the plot, and also where there are the fewest number of data points. In this case, the observed P90 is somewhere around 17, whereas the reported P90 is 25. That is actually quite a bit of difference between the observed and the theoretical model by this family. We can also try a different distribution family to see if there's a better fit. Gamma seems to model a bit better. There's also a Weibull distribution that we can try. So with the Weibull family, the P90 has changed to 19.73, so it's changed by a bit too. The number you get depends on which family you choose and also depends on how well the data is modeled by that family. So as these numbers are reported, there is an assumption of which model or family you have used here and how well the model fits the data. On the FSD Bootstrap tab, we use a more modern method of finding these 3 numbers. The bootstrap or resampling procedure takes a large number of repeated samples from the data to find the P90, P50, and P10 values. This process does not require any assumptions about the families of distribution. This is a fast procedure and also provides an estimate on the variability of numbers as shown with the different curves here. If we want to estimate production at the proposed site of a new well, another approach is to use spatial smoothing. Here we are looking at the spatial pattern of metric EUR values by calculating the smooth interpolated surface. The top plot comes from the advanced analytic algorithms of S+. It is static and cannot be marked. The lower plot shows the same gridded values in Spotfire. We can mark a new selection of wells and calculate a new surface, for example. This smoothing control lets us prune some more detail. Another control allows us to either show or hide the points on the plot. In the production optimization process, a well's location is just one factor that affects this production, or EUR. The completion process itself is an important factor of a well's future production. For example, how many fracture stages or how much sand or fluid is used in preparing the well. This page combines the spatial patterns with regression and what-if analysis. The starting point is the gridded region from the previous page. From here, we can select a region and look at the average EUR for the points in that region. This value would be the expected EUR if we drill a new well in this region and we knew nothing else about the well. Behind the scenes, a regression model studies how the completion parameters affect the EUR and then lets us make changes to our hypothetical well before the well is actually drilled. This process lets us optimize the well production to balance the costs of well completion against expected future returns from a well. After choosing a region, we can then move these controls around and recalculate a predicted EUR based now on both the location and the completion parameters. Spotfire's dimension-free data exploration capabilities enable users to interactively visualize data. For example, we might find that extra fracture stages are only worthwhile in areas of high potential EUR. This page shows the important step of how EUR is actually estimated from the raw production data. As before, we were interested in the potential production of a proposed well site, and as before, we select some nearby wells. Let's choose a few wells to be less cluttered, and then click on Fit Decline Curves. As we select the wells, we see the raw production data shown down below, where time is shown in chronological order. Some wells begin quite a bit before other wells. The objective here is to take this group of wells and represent the production with a single curve known as a type curve. The production data we have selected has been fitted and is shown on the right-hand side down below. The data has all been time normalized, so it will all begin at time 0. Here, each production decline curve is fit using two theoretical models, PLE, or power law exponential, and HYP, or hyperbolic. Both fit pretty well for each of the data curves. The procedure automatically identifies and removes outlying data points. There is a table shown here for the actual model parameters for each of the production curves. Also, the EUR is calculated for each production decline curve. From these curves and their fits, a single type curve is calculated, so any of these individual curves, or the type curve, can be extrapolated into the future for well monitoring purposes or to calculate the EUR. Spotfire's unique abilities enable users to anticipate opportunities and risks by seamlessly integrating predictive models and real-time event streams to move beyond the limitations of historical data analysis. Spotfire uniquely provides prepackaged predictive analytic capabilities, leverages open source and third-party statistical tools, and integrates data at rest with data in motion in order to deliver the 2-second advantage. Thank you for watching this TIBCO Spotfire demonstration. For more information about this example, please contact our Marketing Development Specialists group at mds@tibco.com.